Hello and welcome to the course Signals and Systems. I am Dr. Zishan Karim from Electrical Engineering Department, CUIUA campus. In this video, we will cover the topic Z transform. Let's discuss what is Z transform and what are the advantages of Z transform as compared to the other transforms. Z transform is the most general concept for the transformation of discrete time series. Whereas in Laplace transform, which is the most general concept for the transformation of continuous time process. For example, Laplace transform allows you to transform a differential equation and its corresponding initial value and a boundary value problems into space which the equation can be solved by ordinary algebra. So by using the Laplace or the other transform, we can transform the complex differential equations into the ordinary algebra. So in this way we can solve easily, the calculation will become more easy. So switching of spaces to transform calculus problems into algebraic operations on the transforms is called operational calculus. So the Laplace and the Z transform are the most important methods for this purpose. So the one is for the continuous time series and the other is for the discrete time processes. So these are very much important to transform the calculus problems into algebraic problems. So there is a summary about different transforms. You can see that Laplace transform is represented for signal f of t in this way, 0 to infinity e minus st dt. The one-sided Z transform, one-sided means from 0 to infinity is one-sided. So x of n z minus n for any x of n signal. And the two-sided Z transform of a function x of n, a two-sided means from minus infinity to plus infinity for signal function x of n, you can find the Laplace Z transform in this way. Now, as we look for the relationship between the Fourier transform and the Laplace transform in the previous videos, here we will find the relationship between the Fourier transform and the Laplace transform. So, as you know that expressing the complex variable z, so z is a complex variable as compared to only the uh, omega domain, like in the Fourier transform, there is one omega part, like there is on the real plane, complex plane only, and this is the combination of real and the complex. So note that expressing the complex variable in terms of polar form reveals that the relationship to the Fourier transform in this way. Let's represent the complex variable z in terms of a polar form. Polar means r is the radius e j omega, right? This is its polar form. Omega means theta here, right? So ej omega or ej theta. So x r e j omega equals to n equals to minus infinity to infinity. So x n replace z with the r e j omega and minus n. So put further evaluate r e j omega, x n separate r and e j omega terms. You can get r minus omega n e j omega n. So suppose if r equals to 1, then what will happen? It becomes x e j omega, and we can write x omega, which is similar to n is equal to minus infinity to infinity x n e minus j omega, which is the Fourier transform of x of n. So we can say that by taking r equals to 1, the Z transform is equivalent to the Fourier transform. However, in general, we can say that the Fourier transform of x of n r minus n is equivalent to the Z transform Fourier, sorry, x of n r minus n Fourier transform is equivalent to the x of n Fourier transform, right? So this is a unit circle with the radius 1, and z is equal to e j omega is the complex plane. As you know that the for Fourier transform, it doesn't converge for all sequences. That is, in the infinite sum may not always be a finite. For example, you go from minus infinity to infinity, then its results will not always be finite. So similarly is the case for the Z transform that does not converge for all sequences for all values of Z, right? So set of values of Z for which the Z transform converges is called the region of convergence. So we have to find the set of values of Z for which Z transform converges, and that region is called, or that set of values is called region of convergence. For the Fourier transform to converge, the sequence must have a finite energy. So as we noticed in the previous slide that x of n r minus n is equivalent to the Fourier transform case, but the signal will be x n r minus n, right? For this to converge, it should be less than infinity, right? However, Z transform of the sequence xn is the Fourier transform of the sequence xn r minus n, right? So we can see that the Z transform therefore exists or converges if this condition met. That is, xn r minus n should be less than infinity. So this gives us the condition that it should be less than infinity. So for the existence of Z transform, the region of convergence therefore consists of a ring in a Z plane. So region of convergence can be lie in this side and can be lie in this side, right? Can be lie inside. So it depends on what is the exact value. But from here we can notice that it always lie inside the ring, unit circle, right? Poles and zeros. As we already discussed this in the Laplace transform, here in the situation is almost similar when xz is a rational function. That is ratio of polynomials in Z. Then the roots of the numerator are referred to as the zeros. This one, its roots are zeros, and the roots of denominator is referred to as a pole. Now take an example to discuss how can we calculate the Z transform. So this is called a right side sequence. What is mean by right side sequence? It means that the region of convergence lies outside the unit circle, in this way, right side of the unit circle. So let's prove this by an example. So for example, xn is equal to given signal is a and un. So un means that it is right sided, because un positive, it means it is right sided signal. So the Z transform is given by a n u n z z n z minus n. So this is your x of n, and this is your general equation z minus n. So by combining a and u and changing the limit from 0 to infinity, because here the limit is from 0 to infinity because of unit step function. So a z minus 1 whole n. So by power series, it is equivalent to any term which is from 0 to infinity is equivalent to 1 over 1 minus a, right? Or 1 minus r. So here r is az minus 1. So just replace r with az minus 1. So you can get x z equals to 1 over 1 minus az minus 1. And by further evaluating, we can get, for example, 1 minus a over z. We can write in this way. So it is equivalent to z minus a over z. So 1 over z minus a over z, which is equivalent to z over z minus a, right? And the condition here should be z greater than a. Why? For example, you can notice that a z minus 1, the first condition is that it should be less than 1, right? So less than 1, it is the condition. So to fulfill this, we can write that a over z is less than 1, right? And if we move z to the other side, it becomes z greater than a. So by using this mathematical manipulation or steps, we can get this condition z should be greater than a. If z is not greater than a, then it will not converge, right? Clearly, xz has a 0 at 0 z is equal to 0. If on denominator you see that there is one z, so which is 0 at which is 0, right? Z is equal to 0, and the pole is at z is equal to a. So we plotted here the pole by cross and 0 here at the center. So the region of convergence should be z should be greater than a. So this is our region of convergence, right? If z is less than a, it means it lies inside the circle, then it will not converge. So this is the condition. And other thing you must remember that region of convergence is necessary to calculate in Laplace and Z transform. Otherwise, sometimes it happens that the two different signals have the same result, like same Z transform or Laplace transform. So in this way, region of convergence will separate these two signals. To take another, so let's take another example, which is the left-sided sequence to prove the region, to describe that what is the effect of the region of convergence. So consider xn is equal to minus a n u minus n minus 1. So here unit step is on the left side. So because this is minus side, sign minus n minus 1, right? So it starts from um, minus 1 as well, right? So because it is non-zero only for n less or equal to minus 1 and less or equal to. This is an example of left-sided sequence. So let's take the Laplace transform or Z transform. So put the values a and u n minus 1 z minus n, and general limit is minus infinity to infinity, and the minus sign is due to x of n. And further evaluating, we get minus infinity to minus 1 because it is equal to non-zero for n less or equal to minus 1. So the final limit, upper limit will be minus 1. And by combining these two, a n and z minus n, we have this one because unit step will be equal to 1, right? So further, we change the limit from minus infinity to minus 1. So we just change the from 1 to infinity. So the power will be changed from positive n to minus n and from minus n to positive n. And we can further write this equation in this way: 1 minus n equals to 0 to infinity. We are changing it to 0. The reason is that by power series we can solve this equation easily as we solved for the previous example as well. Because for the power series the condition is 0 to infinity. To make it 0 to infinity, actually it is from 1 to infinity, we have another additional term 1 minus. The reason is 1 minus, for example, when you put n equals to 0, this term becomes 1, right? So for additional n equals to 0 term, we have a 1 value, additional value. So by introducing 1 minus 1, it becomes 0. So it is equivalent to this one, right? From as 1 starting from n is equal to 1. So region of convergence, a minus c inverse c should be less than 1, and uh, from here you can see that z by a is less than 1, right? And when you move a on the other side, it becomes z should be less than a. So here the limit is z should be less than a. So let's solve it further. So 1 minus 1 minus a minus 1z by using the power series as we already discussed. So taking the LCM and solving it once again, you will get the same result like z over z minus a. And here the difference is region of convergence which is less than a. Thank you for listening, and for Q&A session, we have an online separate session. Thank you very much.